So in last lecture, we learned how to implement the semantic segmentation network and also the pose estimation network, okay, using the CNN architecture. So the core of the architecture that is proposed to solve the semantic segmentation is this transpose convolution operation, which does the opposite operation to the convolution operation. So it can upsample the signals, okay, 2D signals, and also it is differentiable, so it can be used in the entire deep learning architecture. And the reason why it is called as transposed convolution is their convolutional matrix is transposed compared to the standard convolution operation. And we are normally constitute this type of encoder-decoder architecture to solve this semantic segmentation problem. Okay, so we call this as encoder-decoder architecture because encoder usually extracts some useful information, which is called as feature. Okay, so low-dimensional vector, we will call that as feature. So first, we extract some features from the 2D images using the encoder architecture, mainly composed of convolutional operation, and then we will apply transpose convolution to upsample it to the same dimensional signal, and we will enforce the same dimensional signal to be the segmentation mask in the semantic segmentation task. Okay, are you guys following this? Okay. And given many X and Y pair, we can anyways train this encoder-decoder architecture to work for this semantic segmentation. Of course, we have to collect manually the segmentation map. Okay, but I mean, if we take time, take effort, we can collect many semantic segmentation ground truths. Okay, so after getting this ground truth, we can anyways train this encoder-decoder architecture. So nowadays, the bottleneck is collecting the data set. Okay, so I mean, collecting this type of map by human effort, that takes a lot of time, but after collecting this, we can just train the network. Okay. And then we also learned image generation things. Okay, so nowadays the image generation, maybe you are using GPT, even GPT to making some images, but that is a slightly different technique. So that is not anymore using the CNN. They are using transformer architecture instead of the CNN. We will also learn about transformer in this class later. Okay. So, but I mean, basically what they do is they are using gradient descent to train the transformer to be trained to generate some images. Okay. In that sense, they are similar, but they are using slightly different architecture, which is transformer. Anyways, this is quite basic things. Okay. And also, the other important difference is now you learned about this adversarial laws, okay, that is proposed to make the network to try hard to generate high quality images. Okay, I already explained the conceptual things about these adversarial laws, but nowadays we are not using these adversarial laws, but using diffusion laws, okay, which is more advanced. And also, this is also not the scope of this lecture. You can maybe take generative model courses in AI graduate school, maybe to further understand these image generation things. Okay. Okay, but that's also similar in the sense that we are using deep architecture, which is differentiable, and that's another loss function called as diffusion loss. Okay, so in that sense, that is also in the similar framework we have learned, but they are anyway different techniques. And also we learned that this encoder-decoder architecture that can be used in the image generation network as well, okay? But nowadays, this part is replaced by the transformer, okay? And this is adversarial loss. And also, this is also being replaced by diffusion losses nowadays because of the accuracy. And then we have learned about pose estimation task. Okay, in pose estimation, we need predefined topologies for how to define the pose. Okay, for example, for the human hand, I already told that there we have to define 4 points for each finger and 1 point from wrist. So this is defining the topology of the hand. And also for the human body, we also have to define 14 or some define the human body as 20 key point. Anyways, for the key point in the human body, we have to define their topologies first. Okay, this would be the key point in the human body. And then from the thing we have to do is we want to train the network that can estimate the XY position or even Z positions of this key point. That's the pose estimation task. And I mean, the naive implementation of this pose estimation would be to replace the later part, the output part of the RLXNet, maybe. Okay, so RLXNet originally they are trained to output the probability vector for example, if we are using ImageNet, we have to estimate 1,000 dimensional probability vector because there are 1,000 semantic classes. Okay, but we will replace that last probability vector with this dimensional vector because there are 14 key points and we will only estimate X and Y coordinate. Okay, so if we replace the last layer to have the 28 dimensional output, then also if we apply the mean square error loss to make their outputs close to the ground truth key point joint coordinate, then we can achieve this pose estimation. Okay, but the thing is, I mean, finding the exact X and Y coordinate from coordinate of this key point, maybe this would be, I don't know, 50, 70, 50 maybe, and this would be like 80, 100, like that. The coordinate, XY coordinate value, that would be like this, okay? Even humans, sometimes it's hard to estimate the exact coordinate values from the RGB images. It is not very intuitive. So if you try to train the neural network that directly estimate the low coordinate values, then it sometimes works, but their accuracy is not that good. Actually, you may feel like that. So in this approach, they are proposing, I mean, another representation as the output of this pose estimator. Okay, so which is called as heat map representation. Okay. So what they do is they just make some, how to say, this red point is the having the maximum value, and blue values, they are having the lowest value. So I mean, if seen in this plane, that would be like this. Okay, so these have the peaks. Okay, and all other have the blue values, which are not the peak. Okay, so this kind of thing is the heat map representation, and for humans, this is more intuitive way to say where the key point located. Okay, so for each key point, if there are 14 key points, then we are making 14 heat maps. Okay, so for each joint, we are estimating where that joint located. Okay, in the spatial images. So that's the heat map representation. And so this is the architecture of them. Okay, so given input image, okay, they are applying several convolutional pulling layers, and they first estimate the heat maps. Here, what they estimate is their heat map. Uh, and also, mm, sure. I'm not okay. Anyways, they are concatenating these estimated heat maps with uh, the another stream of the features extracted from the input image. They concatenate them here. Okay, this means the concatenation, and then apply another convolutional layers to estimate the second heat maps. Okay, and then also do the similar things iteratively. So uh, I think this is more intuitive way to show. Here you can more intuitively see the the pipeline. So from given image, applying several convolutional and pooling layers, you may estimate the first heat map, and then using their another stream of features and the initial heat map by concatenating them and by feeding them to another stream of convolutional and pooling layers, you estimate the second heat map, and then do the similar things multiple times to estimate uh, t t times heat maps. Okay, so that's t is the hyperparameter we can decide, but in the paper t is equal to 3. So we do this type of things 3 times, and we can get 3 heat maps. Okay, so from the overall pipeline, we estimate the first heat map, and estimate using this as the another input, estimate second heat map, and using this as the another feature input, and to estimate the third heat map. And this becomes our final heat maps. Okay. And the thing is, we are applying supervisions, our heat map supervisions, to three of all of these heat maps, intermediate heat maps. We are applying the MSE laws, which makes it close to the ground truth heat map. Are you guys following this? 이거 어려운, it's not difficult. Okay. So anyways, important thing is you can train the overall network because all the component here is differentiable, right? Most of the layers are composed of convolutional and pooling layers, but the paper is saying that if you constitute the architecture like this, iteratively estimate the heat map, then I mean, the post estimation accuracy that could be robust. That's the thing the paper wants to say here. Okay, and we are applying the L2 supervision you are applying L2 supervision for all the output. Okay. Okay. And this is the, the pose estimation network. I mean, this is the network originally proposed the human body pose, but I'm showing the network tuned for the hand pose estimation. Okay. So even though the code is very complex, but you may find that the overall architecture is similar to overall grammar is similar to what I explained before. So this class is composed of two parts. The constructor here, okay, that is defining the, how to say, the structure of the network. Okay, so uh, this network, they are having just one layer of convolutional layers, okay, and one layer of max pooling, okay, and also we are defining the nonlinear layer here, okay. And this part is defining the forward function, okay. So here we are given the images, we are applying multiple convolutional and pooling layers, okay. And then in the intermediate layers, we extract some features, okay. So by applying multiple convolutional and max pooling operation, after doing that, we call the intermediate output as the feature and then map the feature into heat map. So this is the first heat map, okay? And then by concatenating the heat map, the first heat map with the feature we obtained here, okay? We apply another stream of convolutional and nonlinear layers and extract the second heat map here, okay? And then also by concatenating the second heat map with the feature vector, we extract it in the middle, okay? And then apply several layers of convolutional and nonlinear layer. And we estimate the third heat map, actually the final heat map, okay? Are you guys understanding this? Okay. And actually we will apply our ground truth heat map supervision to three of these heat maps, okay? Are you guys following this? I mean, it seems complex at the first glance, but the structure are very similar to what we have learned. Okay. Okay. So using this post estimation architecture, you can uh, achieve the heat map. I mean, you can estimate this type of heat map representation from the RGB image. Okay. So actually, implementing the training code is assignment two, actually. Okay. Using this architecture, you may have to implement the post estimation network. Okay. You have to train them. Okay. Okay. So this is the end of lecture. This is the, slides replicated. So yeah, you don't have to worry about that. Okay. So this is the end of lecture 6. Okay. Mhm. And the next thing I want to teach is the object detection pipeline. Okay, so I mentioned that image classification, object detection, and semantic segmentation, those are three representative applications in computer vision field. And we learned about image classification and semantic segmentation, how we can implement CNN architectures to solve the problems. But the remaining thing is how to solve the object detection using the CNN architecture. Okay, so we will learn about that. So, I mean, semantic segmentation, it seems more complex, okay, compared to the object detection, but semantic segmentation, it could be solved by the encoder-decoder architecture. And of course, there are another approaches, okay? But I mean, this could be anyways solved by involving the encoder-decoder architecture. But this bounding box representation, uh, I mean, for the object detection pipeline, um, I mean, object detection pipeline that requires the object bounding box representation, and it makes us to have the specialized some networks. Okay, so we will learn about that now. Okay, so this is the object detection task, and we are explaining the images and their internal objects using this bounding box representation. And inside bounding box, we have to also estimate which kind of objects are inside. Okay, that's the object detection task. Similarly to the semantic segmentation in object detection task, the naive implementation is very simple if we use the sliding window approach. Okay, so this type you can define this type of bounding boxes, and we can crop the overall images using this type of bounding boxes, and then extracting by cropping the image regions inside, and we can feed these image patches into CNN to estimate their classes. Okay, so by doing this, we can also maybe achieve object detection. Okay, but thing is, in semantic segmentation, we did similar things. Okay, I explained similar things. In semantic segmentation, the situation was better because we classify the pixels. Okay, we classify pixels. So in theory, if the image width and height is like this, then we have to apply this amount of patch operation. We can achieve the semantic segmentation. Okay, but in object detection, the situation is even worse because, um, of course, we have to, if we are given one bounding box shape, we have to apply it by width and height times. Oh, sorry. We have to apply it width and height times, okay, for one object shapes, okay. But compared to the semantic segmentation, it is becoming harder because uh, the bounding box shapes that have to be also buried, okay. So if humans, when we want to detect humans, the bounding box shapes have to be like this, okay? Because the humans, that is mostly standing, and their height is wider than their width, okay? And maybe for some sofa or car object, this type of object bounding box have to be used, okay, to properly explain their shapes, okay. And for each bounding box, we have to apply them by this amount of time, height by width, okay? That takes a lot of time if we use the CNN classifier, okay? Are you guys following this? Okay. So considering their multi-scales, sliding window approach becomes very slow, okay? So it is not practical and uh, I mean, for us, it may take few hours to achieve the object detection from this one image, okay? If it takes too much time, it may be better for us to do this object detection using our hand, okay, without using AI. So this becomes impractical. But thing is, in the year of 2001, indeed, there was some algorithm that does face detection using this sliding window approach. Okay, and before CNN, before deep learning, computer vision approaches are using this sliding window method to achieve this object detection task. Okay, so this is very famous facial detection algorithm that is called as Viola-Jones facial detection algorithm because they are proposed by Viola and Jones. Okay, in 2001, they are published in CVPR 2001, and I mean this is the approach is using this I mean sliding window approach with this sized bounding box, okay, and they extract the cropped images inside the bounding box by I mean searching for patches by this manner, and then region inside the sliding window, they apply it to the shallow learning algorithm called as boosting. Boosting is one of the I mean, machine learning algorithm that is frequently used before deep learning. So it is like SVM or random forest. Okay. Here, region within the sliding window, you first uh, extract the heart-like feature. So it's similar to what I explained before. We extract the human engineered features first and then apply some machine learning algorithm to classify the features. Okay. So, but because it is the object detection task that wants to detect the face, so they apply the sliding window and inside I mean, the patches extracted from the sliding window, they extract the heart-like feature and then apply boosting algorithm. And then they decide whether that patch is face or non-face. Okay. That is the Viola-Jones facial detection algorithm. And also this is already implemented in the OpenCV. So if you search for the OpenCV library, you can find facial detector, and that is actually implemented using this method. But the thing is, anyways, we cannot use this kind of approach because their time complexity is very high. Okay, so the initial idea to make the deep learning algorithm become practical using the deep learning method is using this object proposal algorithm. Okay, so what they want to do is rather than applying CNN, the deep learning algorithm, on all the bounding boxes extracted from the sliding window, they want to find some image regions that are likely to contain the object. Okay, so as I told you, if we extract all the bounding boxes from these images, there would be H by W by types of bounding box, number of bounding boxes will be extracted from the images. And this will be very many. And uh, actually, this is already very small scale images. You are nowadays using even large size images because this is actually the high definition image size. Okay, so now the resolution of the images are becoming larger, and because of that, even extracting the bounding boxes from the whole image that takes a lot of time. Okay, but I mean this is already I don't know, more than this. Okay, two times. I mean anyways, this is very, this 2 million maybe. Yeah, the the number of bounding boxes is very many, but this is the example result of this object proposal algorithm. Here, what we want to do is wanting to extract 1,000 to 2,000 bounding boxes, which may contain the object inside. Okay. There are many algorithms for this, but one famous algorithm is the selective search algorithm. So they are giving us 1,000 bounding boxes that may contain the object inside. Okay. And if we apply CNN operation on this 1,000 to 2,000 bounding boxes, rather than applying the CNN on these 2 million bounding boxes, the time complexity is becoming faster, almost 1,000 times. Okay, are you guys agree with this? Okay, so even though this idea is very naive, but in practice, this helps a lot. Okay. And this is the, I mean, example of the selective search algorithm. So then you may question where the object may appears. Okay. So we are saying that we want to find some regions that are likely to contain object inside. Okay. But how we can discriminate the regions that may contain object or not? That is the next question. And the answer is, uh, if regions are having uh, coherent color and textures or other features, there's high probability to have an object inside that region. Okay, so I mean, in the image, if some regions are having coherent colors, here blue colors are consistently observed. Okay, and or they are having similar texture features. Okay, and their size is more than threshold. I mean, inside the object, these regions are object regions, and they are having coherent color and textures. Okay, so using this type of prior information, this algorithm, I mean, the selective search algorithm, they first apply clustering, color clustering, or anyways, the feature clustering, textureful clustering, or anyways, the clustering on their pixel features. Okay. And these two type of result is showing the clustered regions. So their color is here. Their color itself is not important, but you may have to see if they are having, if each pixel is having the same color, they are clustered into same class. So you are seeing that these pixels with the same color, they are clustered into same cluster because in the RGB space, they are having the same color. Okay. So anyways, but I mean, we already learned about the k-means clustering, right? And in k-means clustering, k was the hyperparameter we have to decide. Okay. There, how to say, uh, how many clusters are inside the images, we cannot decide simply. So when applying this type of clustering, they make uh, multi-dimensional clustering result. Okay, so here it is the cluster map that is obtained quarterly, and here you are seeing that the segmentation map, the clustering map, which is densely obtained. Okay. So here, for example, all the blue pixels, here all the blue pixels are clustered into same class, but here they are having many smaller clusters inside because they are having more number of clusters. Okay. We cannot actually decide how many clusters we will have, but um, we cannot control that. Because of that, this algorithm is making like six multiple scaled clustering map. Okay, and then using that to say, uh, uh, anyways, using this type of multi-scale clustering map, we are somehow wanting to estimate the bounding box using these clusters as the features, as the input. We are actually in the selective search algorithm, they estimate the bounding box, which may contain the object inside. Okay, so, but I mean, you don't understand the details of this algorithm. You may just understand this selective search, they are using this type of multi-scaleness, their pixel, the feature similarity, they are wanting to uh, capture the objectness. Okay, and they are estimating actually 1,000 to 2,000 bounding boxes using this type of prior information. Their assumption is if regions that have similar colors and textures and their size is larger than some threshold, there will be object. There is high probability that the object occurs in that region. So that is their assumption. And indeed, uh, this is the, selective search algorithm, their result, which is implemented in the OpenCV. OpenCV already implemented this selective search. And if you execute that, then you can see that the bounding boxes are extracted around the object regions rather than the background regions. Okay. And among these 1,000 to 2,000 object boxes, there is, of course, some bounding box doesn't contain the object, okay? But if there is one bounding box among these 1,000 to 2,000 boxes, the CNN classifier may discriminate that object, okay? Okay, so if among this large number of bounding box, let's say one object is having object and all others are not having object inside, but in this situation, we can, we are assuming that CNN classifier can discriminate, okay? The thing we want to achieve this object proposal stage is we want to anyways contain one bounding box. We want to secure one bounding box contain an object. And later, using CNN, we can discriminate this from others. Okay. Are you guys following this? So anyways, thanks to this object proposal algorithm, the implementation is becoming more feasible. Okay. Previously, we had to apply CNN a few million times, but now we have to only apply the CNN few thousand times. Okay. So the time complexity greatly improved. So you may remember that in the year of 2012, the AlexNet comes out. Okay, this is the CNN architecture that first achieved the state-of-the-art accuracy in ImageNet challenge. And next year, CVPR conference, the regional CNN, which is called as RCNN, have been proposed. R means regional. And this is the architecture for proposed for solving for object detection task. Okay, original CNN that is proposed for image classification, but RCNN that is proposed for object detection. And we first obtain 1,000 to 2,000 bounding boxes using the selective search algorithm. Okay, and then we here we apply selective search algorithm on the images and crop the images, okay? And then resize it and feed it to the convolutional CNN. Actually, this convnet is same word as the CNN. So we feed these cropped images into the CNN architectures, okay? And then we obtain in the last layers, we may have the feature extracted, and then we train another SVM classifier that can discriminate these features into semantic classes. Okay, are you guys following this? So this is the first approach that is developed for extending the CNN towards the object detection algorithm. So because we already search for the bounding boxes, their candidate that may have the object inside, and crop the regions and apply CNN. Maybe without SVM, we can directly map it to the semantic class, but at this time, I'm not sure. But I mean, this method is also suboptimal, but they used another SVM rather than directly map the features into semantic classes using the CNN framework. They can do that, but they didn't do that. I'm not sure why, but they use another SVM classifier to map these features to the SVM. Okay. That is the RCNN, which is initially proposed in the year of 2013. But thing is, there are limitations. Still, we greatly reduced the number of bounding boxes used. Thanks to that, we can greatly reduce the number of CNN operation. So we could make it feasible, but still very slow. Okay, if you run this code, then for one image, it may take 1 minute to 2 minutes, but depending on the GPUs. Okay, but it already takes a lot of time to obtain one result, one object detection result from one image. It may take 1 minute, then it is not that desirable, so still slow, so there are room to improvement, okay? And also another limitation is they are not end-to-end trainable. So you will see many keywords like end-to-end, which means the CNN architecture normally takes the raw input and output, I mean, without further processing, without many post-processing, we output the final output. Okay, so this is end, the first end, and this is the final end. So normally it is called as end to and trainable when their input and output, the CNN is all using this initial input and final output, then it is called as end-to-end trainable architecture. But here, we are using some selective search algorithm to first initially process the somehow images into some patches, and then we apply SVM later. Okay, so in both direction, I mean here it looks like this. From the image, we are applying selective search, and then there are CNN, and then SVM, and the final output. Okay. So we do not want to this type of heuristics. Okay, we call this as heuristics. So if we are having end-to-end trainable architecture, then all the parameters can be updated to optimally map this input to the output. However, if there are some other architectures like this, which is, I mean, outer to the CNN architecture, that we cannot learn their output, I mean, when training the CNNs. So in that sense, this becomes suboptimal. Okay. So in deep learning research, we always want to achieve this end-to-end learnable capability rather than involving this non-learnable component. Okay. Even though the SVM is learnable, they can learn their parameters, okay, but they are separately learned, okay. CNN learns their parameters, not seeing the SVM parameters, so we anyways call this SVM also non-learnable component, okay, in that sense. And indeed, we humans, when doing the object detection task, for example, this is the human region, right? Human region, but we humans also, if we extract these patches from the entire image and asked to which objects are inside this bounding box, then sometimes, how to say, these patches cannot involve much context. Okay? So for example, this is better situation, but for example, here, we are cropping the regions here and ask humans, any other friend, uh, if this region is whole or not. Then because there are not much context inside the patches, so even humans, their accuracy for object detection is becoming less, okay? But humans, if we are given whole images and some people ask this part is whole or not, then it is easier to say, right? So it is very important to use this whole image signal, even we are asked to classify these small regions inside the images, okay? So starting from these cropped regions and classification, doing the classification using CNNs, that is very limited approach, actually. Okay. So in the year of 2015, uh, there are more advanced architecture introduced, which is called as fast RCN. Okay, so this is we learned RCNN algorithm here, and after that, the fast RCNN proposed. So you can expect that from their name, fast RCNN is fast, okay, and they are accurate, more accurate than the RCNN architecture. Okay, so you will see So this is their fast RCNN architecture. So normally, the CNN is composed of two parts, the convolutional layers and the fully connected layers. Okay, we already learned about this, right? So the first part is mostly composed of convolutional layers that is processing the 2D signals, okay? And fully connected layer, they are doing the flattening on the reduced 2D signal and map it to one-dimensional signal and apply MLP to map it to the class probability. So we only use the first convolutional layers in the original AlexNet or other CNN architectures and apply it to the over entire images rather than starting from the cropped image and applying the entire CNN. Okay. In RCNN, we crop the image first using the selective search result and apply the CNN. Okay. But here we are applying the first layer of convolutional layers on the entire images. Okay. Are you guys following this? Are you guys following this? Okay. Uh, I mean, in 그 object, I mean, for the convolutional layers, in the ImageNet, I mean, for the image classification task, they are using 2 to 4 dimensional images. But here, they are using larger scaled input image. So because of that, if we use the convolutional layers, their how to say convolutional layer that we apply their convolutional layers on the entire image, their output is becoming two-dimensional signal. Okay, so their intermediate result becomes the two-dimensional signals. Okay, and this is because here, originally in convolutional layers, their, how to say, intermediate layer response, that is two-dimensional signal, but they are reduced two-dimensional signal because of stride or pulling. We are normally wanting to reduce the two-dimensional signal. But even the input size here was smaller compared to the object detection task. Okay, previously, normally 2 to 4 were, I mean, the dimension similar was used, but here the low input scale, like this this amount of images are used, and I mean, using the convolutional formula that I mentioned, maybe the output size depend on this type of formula, depending on their corner size, padding size, and stride, and also the input size. The output size is decided, and normally because here in object detection, their input size is in the higher dimension, their 2D signals are becoming to have the higher dimension. And also important thing is, because we are constituting these convolutional layers using the convolutional operation, the features, I mean, these in the original images, these regions features are accumulated in these regions. Are you guys agree with this? And also the features for these images are accumulated in these regions. Okay. So because convolutions, they are I mean filtering operation that applies the filter corners in each local regions. Okay. So their responses, they are having, they are retaining the spatial, how to say, consistency to the original image space. Okay? I mean, this part is having the features for these images, and this part is having the features for this part. They are tending to have that tendency, right? Because of the characteristic of the convolutions. So without applying CNNs multiple times in this way, by applying convolutional layers one time, we can somehow extract the two-dimensional features from the entire image in one-time manner. Okay, are you guys following this? And some people may, I will explain that later. So here we can regard this two-dimensional signal as the two-dimensional feature that is retaining the overall entire image features. And instead of cropping the images using the bounding box obtained from the selective search, we want to crop these features using the bounding box obtained from the selective search. Okay. So in previous RCNN, you may see we crop the images, okay, using the bounding box obtained from selective search. Okay. But because the feature space, it is retaining some spatial information. So this part having the features accumulated for this part, okay? So we can now extract, we can now crop the feature space instead of the image space. Okay, are you guys following this? Okay, so here you can see instead of the image space, we are cropping the feature space. Okay, but thing is, and then we apply the fully connected layers to map those cropped features into each class. Okay. I mean, are you guys following this? But before that, we have to remember one thing. That is, the extracted features, they are in the different size. They are having the different size, right? So here, maybe their bounding boxes are smaller, right? And here, their bounding box is larger than this part, okay? So you can see there are like, for example, 20 floating values, but here there are 40 floating values, okay? Are you guys following this? And here there are maybe, for example, having 29 dimensional floating value. So after extracting these features, we have to apply fully connected layers that may have MLP layer, then map fixed dimensional vector to fixed dimensional vector. Okay, but the features cropped from this region is not having the fixed dimension. So to relieve this problem, we are using ROI pooling method. This is one of the pooling method. This is, I mean, this is not that simple, right? But this is hard part, most hard part. But anyways, ROI pooling, that is region of interest pooling method, okay? Their aim is very simple. They want to map varied dimensional vector into fixed dimensional vector. Okay, that's what they want to do. So, for example, this is visualizing the 2D feature space. For example, this feature space. And here you are seeing the cropped regions like this, okay? And what they do is they are applying 2x2 ROI pooling here, and they select few fixed dimensional value from each region. It is similar to max pooling or average pooling. That's why they are calling as pooling operation. In the max pooling, they are picking only the value which is having the maximum value. So in each region, they can select values with maximum value. In each region, they apply max pooling. Okay, but anyways, they only select fixed dimensional vectors in each region because they are having 4 regions, and because they are picking the fixed dimensional vector for each region, they can secure they are mapping these varied dimensional values into fixed dimensional vector for each region. Okay, so even though their original how to say, this bounding box size, the bounding box obtained from the selective search, that can be, their size could be varied, but inside that, they are dividing the regions and picking the values which have the maximum in each region. So by doing that, by thanks to this ROI pooling, they can map it to fixed dimensional vector. Okay. And then they apply fully connected layer that is composed of MLP that maps fixed dimensional vector to fixed dimensional vector, right? And then they output 2 things. First is bounding box coordinate, and the other is the probability, class probability. So in each region, we have to estimate their class. Which classes are inside the bounding box, we have to estimate. And also in this stream, we are actually wanting to refine the initial bounding box obtained from the selective search. Selective search, it is heuristic algorithm. So their initial bounding box could be inaccurate. So here, using these features, we want to refine the bounding box, at the same time want to classify their classes. Okay, so there are 2 outputs inside, and we are applying 2 types of losses because there are 2 types of loss output. So we are applying 2 types of losses. So here we are making that, we are writing the things I mentioned in the formula, mathematical formula. So here, this is denoting the probability for K classes. Okay. P is the probability vector for K classes, and this is denoting the bounding box information. This is the center position of the bounding box, and this is width and height of the bounding box. Okay, so when describing one bounding box, we always have to specify their center position and their width and height. And these 4 parameters are deciding that. So we actually have to estimate this T mu from this linear layer. This is the bounding box information we will estimate. And this is the probability vector we will estimate for this part. Okay, are you guys following this? So I said fully connected layer is class probability and bounding box. That is meaning these 2 outputs. Probability vector is k-dimensional vector that is retaining probability, and bounding box information, that is the x and y coordinate, center coordinate of the bounding box, and their width and height. Okay. And this is the loss. Okay, this is same formula for cross entropy loss. So we are applying a log function on that. Okay, and I mean summing over all the output. And this is the error loss, but in this paper, they are proposing smoothed error loss. Error loss, how to say, mm, error loss is actually L2 loss is same as mean square error loss. So we are closing the ground truth and our prediction using this often scared loss function. Error loss is we are closing prediction and ground truth using just absolute, how to say, not scaling them, not scaling their distance, but reducing their absolute value. That is the error loss. We call that as error loss. But here they are actually combining these two. So if you draw this graph, that is actually meaning like this. So they want to apply L2 loss when ground truths and their predictions are very close, okay? But they want to apply error loss uh, if ground truths and their predictions are relatively far. So, I mean, L2, their graph is like this, but they are applying L2 only when their values are small. But if they are far, then they want to apply error loss. So this is practically working good for the object detection, their bounding box estimation. So they are using this loss, but you can regard this as just L2 or error loss. They are somehow, I mean, combining them, but not much gain actually. So you don't worry about too much about these things. So you can regard this as just L2 or error loss. Okay, anyways, they are using these two types of loss that can close the probability, I mean, their probability towards the ground truth and also the localization loss that wants to make their bounding box prediction close to the ground truth. And here you can see their outputs are two things, the probability vector and also the refined bounding box. Okay, are you guys fine understanding this? But you don't have to implement this actually. Object detection pipeline that is quite complex. Okay. So you can just remember these key concepts. Okay. You don't have to worry about implementing everything here. Okay. But important thing is remembering the ROI fully. Okay. Just I mean, want to map some varied dimensional vector into the fixed dimensional vector, okay? And changing of these things. So previously, all the researchers are thinking about these things, okay? But important paradigm shift here is we can now use the full images when detecting when discriminating classes in these small patches that I mentioned as I mentioned earlier. So here because we are mapping the features that accumulate the information nearby. Okay, in these regions, their features are accumulated here, and we are mapping these features to bounding box and class information later, right? So in that sense, it is similar to what I mentioned previously. This situation, this RCNN is asking humans by cropping these regions and ask if this region is holding the holes or not. Okay, the pattern is like that, but here because this region's feature is accumulating the features from nearby regions. So this is more like what I mentioned before. When asking these small part regions if they are belonging to host region or not, it is retaining some information nearby already. Okay, so we can somehow exploit some contextual information from the whole image. Okay, are you guys agree with this? Okay, so here you can see now it is becoming end-to-end trainable. So from the whole image, we use the differentiable CNN component and map it to the final output. Okay, all the component here is differentiable, right? So now we can say it is end-to-end trainable architecture. Okay, but sorry, the time is very over. Sorry. So later, we will further learn about this faster RCNN. That is faster algorithm compared to the faster RCNN, having more, solving few more problems in the fast RCNN. Okay, so we will review that in the next Monday. Okay, thank you.